In episode 30, titled Math for Modeling, Vectors, Matrices, and What Linear Algebra Enables, the goal is to build linear algebra intuition without drowning in symbols, because DataX rewards conceptual clarity about what the math operations accomplish.
You do not need to prove theorems to pass the exam, but you do need to recognize the objects that modeling methods manipulate and the kinds of transformations those methods perform.
Linear algebra is the language that turns datasets into structured objects, turns operations into repeatable transformations, and turns modeling into something you can reason about systematically. When you understand vectors and matrices as representations of data and transformations, regression, dimensionality reduction, and neural networks stop feeling like unrelated topics. Instead, they become different uses of the same building blocks, which improves both recall and decision-making under pressure. This episode focuses on the meaning of vectors, matrices, and a few core operations that show up everywhere. The objective is to make you comfortable translating a scenario into the math language that supports modeling choices without getting stuck in abstract notation. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series.
A vector is an ordered list of numbers that represents a point, a direction, or a feature set, and the exam expects you to recognize that it is the basic unit of numeric representation.
If you have a single observation, like one customer or one device, you can represent its features as a vector, where each position corresponds to one feature value. This makes the idea of a data point precise. It is a location in a feature space, where each feature is an axis. Vectors can also represent directions, such as the direction a model parameter set points in a space of possible solutions, which is why optimization and gradient methods speak in vector terms. The key is that vectors are ordered, meaning the position of each number matters because it maps to a specific feature or dimension. In DataX scenarios, you can think of a vector as the numerical fingerprint of one record, where the fingerprint has a consistent structure across records. When you adopt that intuition, many model behaviors become easier to understand because they are comparing, combining, and transforming these fingerprints. A matrix is an arrangement of vectors that represents many observations or a transformation, and it is the natural structure for organizing datasets and model operations. If you stack observation vectors for many records, you form a matrix where each row corresponds to one record, and each column corresponds to one feature. This is the standard data table you already know, but in matrix form it becomes something you can multiply, transform, and decompose. Matrices can also represent transformations, where multiplying by a matrix applies a consistent linear change to vectors, such as rotating, scaling, or projecting data. That dual role is important. Matrices are both containers of data and operators that act on data. The exam often expects you to recognize that models operate on matrices because models are applied to many records at once and because transformations must be applied consistently. When you view a matrix as organized data or a reusable transformation, you can reason about why certain methods require matrices and how preprocessing becomes a sequence of matrix operations. The dot product is one of the most central operations, and a practical way to understand it as weighted similarity between vectors. When you take the dot product of a feature vector with a weight vector, you combine the features into a single score, where each feature contributes according to its weight. This is the heart of linear models, where a prediction is often computed as a weighted sum of feature values.
The dot product also has a geometric meaning. It relates to how aligned two vectors are, meaning it is larger when vectors point in similar directions and smaller when they are orthogonal or opposed. That alignment intuition is why dot products appear in similarity search, recommendation, and embedding comparisons, where you want to measure how similar two representations are.
In DataX terms, the dot product is the operation that turns many features into one score in a controlled way. The exam rewards this intuition because it helps you understand how linear models make predictions and how feature weights influence outcomes. When you can say that a dot product is a weighted combination that also reflects similarity, you have the right mental model. Matrix multiplication can feel intimidating, but its meaning is straightforward when you see it as chaining transformations and combining features in a consistent way. When you multiply a data matrix by a weight vector, you apply the dot product operation to every row, producing a score for every record at once.
When you multiply two matrices, you are composing transformations, meaning you apply one transformation and then another, and the result is a combined transformation that does both in sequence. This is why matrix multiplication is the engine of neural networks, where each layer applies a transformation to activations, and passing through layers is a chain of matrix multiplications and nonlinearities.
It is also why dimensionality reduction can be described as multiplying by a projection matrix, because you are mapping high-dimensional vectors into a lower-dimensional space. The exam is not asking you to compute these products by hand, but it is asking you to recognize that matrix multiplication is how models apply consistent linear combinations at scale. When you see matrix multiplication as apply the same transformation to many vectors, it becomes a practical concept rather than a symbol exercise. The connection between matrices and datasets is a foundational translation skill where rows represent records and columns represent features. This framing explains why feature engineering changes the number of columns, why adding a feature expands the matrix width, and why adding more data expands the matrix height. It also clarifies why missing values and inconsistent scaling cause issues, because matrix operations assume consistent meaning across columns and comparable numeric behavior when combining values. In many DataX scenarios, you are implicitly working with a data matrix, even if the prompt describes the data as a spreadsheet, a table, or a dataset. When you translate the dataset into matrix language, you can reason about operations like normalization as column operations, and about joining datasets as constructing a larger matrix with additional columns. This translation also supports thinking about model inputs and outputs, because the model expects a consistent matrix shape and consistent feature ordering. DataX rewards this because it makes you less likely to make errors that come from treating features as interchangeable or from ignoring the need for consistent preprocessing. Linear algebra underlies regression, principal component analysis, and neural networks, which is one reason the exam benefits from a unified intuition rather than isolated memorization. Regression can be viewed as finding a weight vector that best maps input vectors to outputs, often by minimizing error, which relies on matrix operations and solutions that depend on matrix properties. Principal component analysis, often shortened as PCA after you have said principal component analysis the first time, can be viewed as finding directions in feature space that capture the most variance, which involves decomposing a matrix into meaningful components. Neural networks can be viewed as a sequence of matrix multiplications that transform inputs into representations with nonlinear steps that add flexibility. You do not need to derive these methods, but you should recognize that they share a core idea: represent data as vectors and matrices, then apply transformations to extract patterns. The exam rewards this recognition because it makes it easier to answer questions about what these methods do and why they behave as they do. When you see linear algebra as the shared engine, you reduce cognitive load and improve recall. A practical skill is translating a dataset story into matrix language verbally, because that is how you connect scenario descriptions to model structure.
If a scenario describes 1,000 customers with 20 features each, you can describe that as a matrix with 1,000 rows and 20 columns, where each row is one customer's feature vector. If the scenario describes adding a new engineered feature, you can describe that as adding a column, which changes the matrix shape and changes what the model can learn. If the scenario describes comparing customers for similarity, you can describe that as comparing their feature vectors, using operations like dot products or distance measures. This translation helps you reason about computational cost and about which methods are appropriate, because some methods scale with number of rows, some with number of columns, and some with both. The exam may not ask for dimension counting explicitly, but it does test whether you understand data as structured inputs and how methods operate on that structure. When you can narrate the matrix representation cleanly, you demonstrate the kind of conceptual control DataX rewards. Norms are length measures that support distance and regularization intuition, and you can think of a norm as the size of a vector in a chosen sense. The most familiar idea is Euclidean length, which measures straight-line distance in a feature space, and this connects to similarity and clustering reasoning. Norms also show up in regularization, where models are penalized for large weight vectors to encourage simpler solutions that generalize better. A large norm for a weight vector can imply a model that relies on large coefficients, which can be sensitive to noise and can overfit, while a smaller norm can imply a more stable mapping. The exam may describe regularization goals, stability goals, or distance-based methods, and norms are the underlying concept that ties those together. You do not need to compute norms for exam questions in most cases, but you should recognize what they represent and why they matter. When you see norms as size that influences distance and penalty, you can interpret regularization and similarity questions more confidently. Orthogonality describes independent directions, meaning vectors that do not overlap in the information they represent, and it is helpful for decomposition and interpretability. Orthogonal directions can be thought of as perpendicular axes in space, where movement along one direction does not imply movement along another. This matters in dimensionality reduction, where you want components that capture different aspects of variability without redundancy. It also matters in feature reasoning, where highly correlated features overlap in direction and can create redundancy and instability in some models. The exam may ask about independent components, decomposition, or reducing redundancy, and orthogonality is the geometric concept behind those ideas. When you treat orthogonality as no shared direction, you can understand why decompositions aim for orthogonal components and why orthogonal features are easier to interpret. This also links to multicollinearity concerns, where features are not orthogonal and therefore create instability in coefficient interpretation. DataX rewards this because it connects geometry to practical modeling behavior. Rank is another concept that the exam may test conceptually, and it is best understood as information content rather than just the size of a matrix. Rank tells you how many independent directions or independent pieces of information a matrix contains, which affects whether problems are well posed and whether solutions are unique. If a dataset has redundant features, the matrix can have lower rank than its number of columns suggests, meaning some features are combinations of others and do not add new information. Low rank can also occur when data is limited or when measurements are constrained, which can make certain models unstable or certain decompositions less meaningful. The exam may frame this as redundancy, lack of independent signal, or inability to resolve unique effects, and rank is the concept that underlies those limitations. You do not need to compute rank in the exam context, but you should understand that it reflects how much independent structure exists in the data. When you treat rank as how many independent dimensions are really present, you can reason about feature redundancy and model identifiability more clearly.
A key to success is avoiding overthinking proofs and focusing on what operations accomplish, because the exam is measuring applied understanding, not formal derivation. You want to know that vectors represent feature sets, matrices organize many vectors, dot products create scores, and matrix multiplication applies transformations at scale. You want to know that norms measure size and support distance and regularization, that orthogonality supports independent components, and that rank reflects independent information. When you hold those functional meanings, you can answer scenario questions about why a method behaves the way it does and what a pre-processing step is accomplishing. The exam's goal is to see whether you can choose the right mental model, not whether you can reproduce a textbook proof under timed conditions. This is also why verbal translation matters, because you can explain operations in terms of their effects on data and uncertainty. DataX rewards learners who keep the focus on purpose and consequence, because that is the exam's practical orientation. When you interpret operations by what they do, you become faster and more accurate.
A useful anchor for this episode is that vectors describe, matrices organize, and operations transform meaningfully, because it captures the entire linear algebra story at exam level.
Vectors describe one record or one direction, giving you a consistent way to represent features.
Matrices organize many records or a transformation, letting you apply operations consistently across a dataset.
Operations like dot products, norms, and matrix multiplication transform those representations, producing scores, distances, projections, and learned mappings.
This anchor keeps you from getting lost in notation, because you can always return to the role of each object and operation.
Under pressure, it also helps you connect a scenario to the right math concept, such as similarity, transformation, or decomposition.
DataX rewards this anchor-driven reasoning because it is repeatable and reduces confusion across modeling topics.
When you can state what each object is for, you can navigate exam questions that mention these concepts.
To conclude episode 30, describe one operation's purpose and then name where it appears, because that is the fastest way to solidify meaning.
You might describe the dot product as turning a feature vector and a weight vector into a score, and then name regression as a place where that appears.
You might describe matrix multiplication as applying a transformation to many records at once, and then name neural network layers or dimensionality reduction projections as places where it appears.
You might describe a norm as measuring the size of a weight vector, and then name regularization as a place where it appears to discourage overly complex models.
The key is to keep the explanation focused on what the operation accomplishes in the modeling workflow, not on abstract symbolism.
When you can connect operation purpose to a familiar method, you show the integrated understanding DataX rewards. If you can do that consistently, linear algebra stops being intimidating and becomes a practical map for how models work.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.